see how that works too. So it's just a brief preview of calculus. I don't know that too much of this would be, really any of it would be quiz material, but we're going to just lay a brief foundation for this. Hopefully this will connect your pre-calculus with calculus, and we'll be able to move forward well in the coming days. So calculus is the mathematics of change. All kinds of different change, amounts of change, rates of change, things like that. With calculus, we can find the slope of a, what would you guess goes in the blank there? Slope of a, say again? Okay, we'll get to that in a second, but in general, isn't it easy to find the slope of a line? You've been doing that for a long time. But now we can find the slope of a curve. We can find the slope of a curve instead of just only lines. We can find the blank rate of change. Instantaneous, yeah. Pretty powerful tool. So the instantaneous, I'll just put instant right there, instantaneous rate of change. We can describe how the curvature of a graph changes from concave up to concave down, how steep it is, how not steep it is. We can find the area under a curve. This is one of the more fascinating things. You're all, I'm sure, very good at finding areas of squares and rectangles and triangles. I think most folks at this point can do that very easily. But what about the area under a parabola? Why would you care, and how could you do it? That's one of the things that we work on. Crazy, strange volumes, like you wouldn't believe. Work done by a variable force. These are all applications of things that we can do with calculus. And there are two really great questions with calculus. There's the tangent line question and the area under a curve question. So the tangent line problem, finding the equation of a tangent line, really comes down to finding, well, let me ask you guys this question. I'll probably ask you guys this question 1,000 times this year. Not because you don't know it, just because it's really important. What are the two things that you need to have in order to find the equation of some line? Slope and a point. If you know those two things, you can find the equation of a line. So having a point is not typically the challenge. It's finding the slope, right? So finding the slope of a curve is really what's going to present us with the biggest challenge. Oh, I thought you had a question for me. It's all good. I just saw you out of the corner of my eye. And so this is a kind of a nice graphic of what a tangent line is. I'm going to draw a different line. Can you guys tell me what kind of a line that is? That's a secant line, right? So a secant line intersects the curve in 2 points. Tangent line intersects in 1 point, and it matches the slope at that point of tangency. We'll talk about secant lines as well as tangent lines. We can approximate the tangent line at this point by using that secant line. Here's the graphic for that, sorry. And then the concept that you probably heard in pre-calculus was, what if we took those 2 points on the secant line and did what with them? We made them get really close, right? So instead of this far away, what if they were this close? Then what if they were this close? And what if we got them so close that the distance between them was approaching 0? They'd almost be sort of the same point. What would that be? That would take the secant line from being a secant line and turning it into a tangent line, right? So there's a lot of details that go into the get the points closer and closer and closer and closer. And it gets really complicated. We're not going to do really anything with that. Just know that there's this thing called epsilon delta. If you ever take a college class, and I will say this, if I were you, that would be a motivator to do really well in this class, because if you do well in this class, you don't have to take Calc 1 in college. And in Calc 1 in college, they always do epsilon delta proofs, which are really unpleasant. So just do really good now, and you don't have to do those. So anyway, just hopefully a helpful hint there. And then as the 2 points get closer and closer and closer, we get to that tangent line, and we will spend a huge amount of time dealing with tangent lines and all different shapes and forms and what they mean, what they do, and what we can do with them. The other one that is just, for me as like a beginning calculus student, I was always just fascinated with the area under a curve. Looking at something like this, what do you think that graph is if you just had to guess?
Cubed.
Cubic, yeah, like x something cubed, right? Plus something squared, whatever. does look sort of like a cubic. And if somebody gave you an assignment to try to find the area under that curve, wouldn't it be pretty reasonable to use some shapes that you know? That's a terrible rectangle. Let's go with that. Use some rectangles to, if you filled the whole thing with rectangles, wouldn't that be like a sort of okay approximation? I mean, depends on your definition of okay, but it would be a reasonable approximation, wouldn't it? Okay, so then the idea is if you did this, obviously it's not accurate. What could you do to make it more accurate?
Maybe triangles.
You could put, okay, I can live with that. So if we put little triangles on top, what would that turn those shapes into? They wouldn't be rectangles anymore. What would they be? They'd be trapezoids. Yeah, so trapezoids are often really good approximators. But let's take that out of the equation. Let's say that we're dedicated to using rectangles. How could we improve our approximation using rectangles?
Make the rectangles infinitely thin.
Yeah.
Thinner.
Well, I don't know if we can make infinitely thin rectangles, but thinner, right? So in this little space that I have, instead of putting 3 of them, what if I said, you know what? I don't want to put 3 of them. I want to put 6 of them. So then they'd be a lot skinnier. And you can see that by making them really skinny, then that little space on the top, it was pretty obvious before, is a lot less obvious now, isn't it? There's a lot less of an error there. And I think that would be a better approximation. And going down the path that you did, well, how could we make it the best? Well, what if we took the number of rectangles and made them approach infinity? If that were the case, then how wide would they be? They'd be approaching 0 width. They'd be approaching just a point wide, and we can then use that to find the exact area under the curve. Exact, not good or better or best, but exact. Okay, I think that's it as far as the introduction goes. So what I do here, you can see like the video is just rolling here, right? So I just hit, at this point I just hit